Hi, everyone. Welcome. Thanks for joining us, the textbook reading group. And today we were going to look at chapter two in the first half of the textbook. Um, and I, I gave this kind of introduction of the book a couple weeks ago for chapter one with another sort of group of folks, but a brief recap is that the first half of the book is essentially providing sort of theoretical foundations for active inference and kind of covering a lot of the various associated fields and theories. So we introduced to the Bayesian brain hypothesis. We're told about predictive coding and message passing in chapter five and all of these different things. Markov blankets come up later. Um, and then it's in the second half of the book that's more about direct modeling. And so with what Daniel mentioned earlier, I'm curious about it sounds like he just made this, so probably a learning resource that would be useful for anyone who's interested in getting into the coding themselves. Uh, but yeah, so for chapter two, following from chapter one, this is where we start taking the low road to active inference, and this is starting with sort of a Bayesian framework. And so, for those unfamiliar, um, Bayes' rule is essentially a rule that describes how we can kind of update our beliefs, our prior beliefs about a given phenomena, given that we have some kind of joint distribution, which is a generative model that can be used to predict phenomena. So, whenever we take a joint distribution, for example, the probability of x comma y, so two random variables x and y, we can kind of decompose that into this nice, really sort of concise theorem that is known as Bayes' theorem, that if we are able to update particular components of that, then it allows us the appropriate rules for updating the other components, such as if you have a X representing beliefs about hidden states of the world, and you have Y, which is observations received from that world, then based on new observations, you can then update your beliefs. So given a new Y, you can update your beliefs about X and the relationship between X and Y. That's sort of the general framework. It's used very broadly. It's existed for decades. It's used very commonly in all kinds of fields, machine learning, like financial modeling, very much used in neuroscience as well, not just in an active inference framework. So again, it's just kind of speaks to the interdisciplinarity of active inference and sort of the depth of how far it's traced itself to roots in various other fields. Um, and so the second chapter largely sticks with that. We get introduced to other concepts such as surprise and Bayesian surprise, which are unfortunately and slightly confusingly at first glance, like they're two distinct concepts. Um, I find them interesting to think about in that Bayesian surprise would be taking the what's called the Kullback-Leibler divergence between posterior distribution and prior distribution. So it's kind of like saying, okay, we received a new observation, we update our new beliefs, our posterior beliefs. How different are our new beliefs given that observation versus our prior beliefs that we had before we received that observation? If they're very different, that means a lot of belief updating needed to happen, right? So what could happen is that they provide this as an example in the textbook. But if you were to strongly commit to a particular belief, if the weighting was such that you were fully convinced that you were not hungry, you are sated in like a categorical probability distribution of, am I hungry? Am I sated? Um, like if you were fully convinced that you were sated, then that means that if you received an observation such as, oh, your stomach is growling, which would, you know, we could speak about that like we might think intuitively, oh, that would mean you must be hungry, right? But if someone were really fully convinced with like a full probability of one that they were sated, regardless of any new incoming observations, then your posterior beliefs will still be that you are sated despite receiving that observation. So it's kind of like um, even though you might not expect to receive this observation that you know your stomach is growling, you're still firmly convinced that you're sated, and therefore no belief updating happens. Um, I recommend looking at that. I think it's in box 2.2. But this idea of Bayesian surprise of how much belief updating happens versus surprisal itself, which is a bit simpler. It's just the marginal probability of a new observation. So, like, given a generative model, how well does that model predict that your stomach's going to growl? You know, and that's it, right? So that just that. So it has nothing to do with your beliefs about if you're hungry or if you're sated. It has nothing to do with X. It's only the Y. So which is why we call it a marginal probability. You know, marginal meaning we kind of can decompose the model into just these marginal parts. So surprisal is really just the negative log probability of an observation that you receive. So you could receive so it could be very surprising to you that your stomach is growling, and yet you are highly convinced that you're sated nonetheless, right? Um, I like this example because for those who are interested in the field of computational psychiatry, which there are many who come into this field, come into active inference because they're interested in or studying computational psychiatry and are looking to kind of add more tools to their toolkit or another framework, which I think that active inference is it's very wide, and I think it brings a lot to computational psychiatry. You can imagine that someone who does not in everyday terms, does not listen to the new observations that are coming in. You know, their stomach is growling, and yet they believe they're sated. It's not terribly far away from very common, you know, definitions of what it means to have delusional thinking or an inability to update one's beliefs despite evidence to the contrary, which is kind of widespread in a lot of sort of psychopathologic like symptomatology, right? So, you know, someone with schizophrenia or someone who is hallucinating, who's fully convinced that something is there, whenever it's not, right? Or someone might tell them that it's not, but that, you know, thus providing them with contradictory evidence to their beliefs, and yet they still hold. So, um, it's more difficult in the case of hallucination because in the case of hallucination, you are in fact receiving an observation that something is there, right? So it's a reminder that this is not simply a sort of prefrontal cortex only sort of, oh, I just have to change the way I think and I'll be fine. This refers to kind of deeper like aberrances in the brain and in sort of neuronal message passing, right? And so things that can happen that can end up producing a hallucination. So that's why I kind of point to like, okay, well, you can receive very surprising observations, and yet there's no Bayesian surprise in the sense that you could still not update your beliefs, right? So there's belief updating, and then there's what the model actually predicts. Um, those are sort of some of the core aspects of kind of understanding the low road to active inference and the Bayesian framework. And then it's in especially later chapters, chapter 4, where we're introduced to expected free energy and different breakdowns of free energy. Um, Chapter 7, which starts talking about matrices and sort of these categorical probability distributions. So actually taking Bayes' rule and actually putting it into a model that goes beyond just having a likelihood. So, so chapter 2 is for anyone who's new to a Bayesian framework, it'll be a significant amount to digest. For those who are already familiar, they're not going to receive anything too dramatically new until they start getting into later chapters and looking at how the Bayesian framework actually comes into more full play in active inference. I noticed that someone's hand was up over time, and so
Yeah, is that okay if I jump in? I think these
yeah.
you have great explanations here, and I really appreciate that. Trying to get an understanding of how we get from Bayes to active inference, but my question is you were talking about the KL divergence. I was thinking of it as being the distance between the Q, which is like the approximate posterior, and the actual posterior. But if you're saying it's the difference between your prior and the posterior, I can wrap my head around that a lot better. It's just sort of the cost of your belief updating. Is it? But maybe I'm confused. Which is which? Is it the prior to the posterior, or is it the approximate posterior to the true posterior?
Yeah. Yeah, no, I see what you're saying. And it depends on like kind of the modeling situation at hand, is how I would say that. So the formal kind of definition, the way it's described here is the posterior and prior. Like that's what's given in chapter two. But then that said, like in whenever you're actually implementing this within a model, it's there that it becomes significant to look at the other perspective because in chapter two we're not actually yet getting into variational methods, right? So we're not looking at an approximate posterior. So what you can do is that you can in very simple examples like the frog and the apple example that we're given, for example, you can it's very tractable to just directly compute surprise and Bayesian surprise, right? Like you could do it by hand. So it's in those cases like there is no variational posterior even computed in the first place. You're just given it like an exact posterior, right? So it's whenever you start getting into using the variational posterior that this kind of additional dimension of looking at things and then actually if it were the case that like say your model itself contains like what it believes to be the true set of beliefs and then meanwhile, you're using this variational method to update a variational sort of posterior. Then you could use KL divergence to try and compare but that would still be respective to that model. Right? Does that make sense? Yeah.
Yeah, I think so. Thank you so much for clarifying that.
Yeah.
And
Yeah.
when we get to the variational part, then I'll probably have more questions. But for now, this is great. Thanks so much.
Yeah, no, absolutely. And I totally welcome questions, and I think that usually they end up providing a lot more information to other people who might be considering the same thing. Um, and and yeah, that's that's sort of a big move to start using variational methods in the first place. You're just like kind of in a qualitatively different paradigm, even though doing exact Bayesian inference versus variational Bayesian inference, it's like, oh, they share the Bayesian inference part, right? But uh but yeah, once you start using variational, it's like there's a couple additional assumptions that get made along the way whenever using variational methods. For anyone who's into computational modeling and kind of like really breaking that down thoroughly, that does mean that unfortunately, you do have to rely upon a couple of extra assumptions in order to view the outputs as valid. One way of doing variational Bayesian inference is to use this kind of active inference framework and the particular ways that they do that. So you'll see in later chat, I don't think they get into it in chapter two at all, but later they'll start talking about how free energy itself, the way that sort of works is a variational method is that um, using what's called Jensen's inequality. So I'll kind of speed it up because there will be more to get into whenever you read about it in later chapters. But it's kind of like by using particular mathematical, I hesitate to call them tricks because they're not tricks, like they're like proofs. But still, it's like by being able to exploit particular aspects of the mathematics, you're actually able to create an upper bound on surprisal. And so even though you can't directly compute surprisal, you can at least compute an upper bound on it. Meaning like, well, if you can continue reducing that upper bound, then you're getting closer and closer to actually minimizing your surprisal as well, for sure. And so that upper bound is itself free energy and it is tractable, right? So that's the entire intention of using variational methods is to just render a lot of these computations tractable and possible and perhaps even more efficient than in cases where you just wouldn't be able to because you're trying to do exact inference. Um, it's also very relevant for those who are concerned with like biological plausibility of these models. It fits really well with different kinds of research in that area because, of course, like the notion that the brain computes exact Bayesian inference whenever we know that many of these problems are not tractable, just it doesn't hold up very well in like kind of a realistic sort of setting. And so part of the biological plausibility is this aspect of the theory or framework of active inference that we there must be something variational going on. So to speak, right? Being able to kind of use mean field approximation and marginalizing out different components of a model and updating them, potentially separately or using these intricate message passing schemes. So the goal is to sort of render intractable problems tractable while simultaneously cohering with research that has been done on the brain and how message passing seems to occur, how neurons seem to communicate with one another. Um, Most research, even outside of active inference, tends to view this as like a kind of hierarchical message passing process. There are multiple systems that are kind of passing messages. So we have these kind of descend and similarly, there will be more kind of mechanical aspects of this. I think especially in chapters 4 and 5, and definitely 5 for anyone who's interested in actually like aligning this with like deep pyramidal cells and like the kind of the more neurobiological aspects. Feel free to skip ahead to chapter 5 if you feel like you have a comfortable grasp of everything prior to that chapter. But yeah, so being able to kind of have these things cohere with the brain while simultaneously keeping it tractable, um, yeah, is the gist. So, anything else I would kind of highlight about chapter 2 because there's quite a bit going on, and actually I realize now we do get introduced to expected free energy already in chapter 2. And we're introduced to variational free energy. So um, I'll I'll just make a couple comments that both of them are variational methods. So we do have variational free energy and expected free energy. They are, in fact, two different ways of computing free energy. Variational free energy would be sort of relative in real time to the model, given where it is at, versus expected free energy, which hinted at by the word expected, is sort of a free energy of the future, so to speak. Expected free energy is what's used whenever an agent does what's called computing policies. So anyone who's familiar with reinforcement learning, that will become, or that'll be very apparent. Like whatever your intuition says, it's correct. Policies, or you can think of policies as actions, or more precisely, sequences of actions. Right. So if you think of like a discrete case, like a mouse in a T maze, and it can choose to go left or right. And then there's also like another space it could go to. So a policy might be, move to this part of the maze, then move to the left arm of the maze over the course of like 2 time steps, like sort of into the future, right? And so that doesn't involve only computing variational free energy in the moment, but it actually also includes predicting what will I expect in the future. And that's where expected free energy comes in and why it's relevant to have this second equation that it's highly related. They're both variational. They're both using the same components of the model, which you can liken to everyday concept. A likelihood model is very similar to what allows us to have perception. and then having a state transition matrix is very comparable to the idea of just having a temporal dimension, having an understanding of like, well, this led to this. So then I can predict that this will happen next if I do this. Like having that kind of temporal dimension of how you relate things. So yeah, with expected free energy, also important there is that uh, we can interpret expected free energy a little bit differently than a variational in that whenever we look at um, it's equation 2.6, and I apologize, usually I share my screen, but I've been having some issues with that today. Um, but equation 2.6, which is on page 33, and it's a bit of a hefty equation there, but it's really just being broken down in multiple ways. And I think especially that first line where we're looking at information gain and pragmatic value. Interestingly, as opposed to variational free energy, where we really just think of this as well, we're trying to reduce complexity while improving accuracy. Here with expected free energy, we're trying to maximize two terms, which each of which are scored negatively. They're both multiplied by -1. So technically, by maximizing these respective terms, we're minimizing or reducing the overall quantity whenever we put them together and multiply them by each by -1 and then combine them. Um, so information gain and pragmatic value. Pragmatic value is significant in that there's this component C that we can see there. The C is a representation, a probability distribution of the observations that the model expects. Um, just as a prior. So it's like a prior over observations. So the way that this is formalized in active inference is to say that um, priors over observations, they tend to get likened to the idea of preferences, and not necessarily preferences in an arbitrary sense, like, oh, I prefer this kind of dessert versus this kind. Um, Preferences also strongly relate to the notion of something like homeostatic set points, for example. So if you had a kind of continuous space like predictive coding model that had to do with an agent's beliefs about its blood oxygenation levels, right? Or its heart rate. Um, Having preferences over sort of like well-regulated levels for those different kinds of physiological measures would be really crucial for the agent's survival, right? So or even just bringing up the hunger, like the kind of slightly silly but still very real example I brought up earlier of like your stomach growling or not. Like we tend to prefer our stomachs aren't growling. I don't want to put it in such an arbitrary sense because there's no assumption that like you are like fully consciously rationally thinking of things in this way. It can be that different parts of the body, different parts of the brain, depending on how you want to sort of divide up the Markov blanket, as it were, each one of them having their own kind of processes and sort of inner model involved, can have their own sort of, so to speak, preferences or priors over observations that they would need to achieve through action in order to maintain the overall organism's survival, right? So the for those interested in like, sort of chaos theory or dynamics or just looking at like non-equilibrium steady states, this is very relatable to the idea of an attractor, right? So whenever you take these sort of attractors or the brain, the body is attracted to, having the body at roughly 98.1 degrees Fahrenheit, is sort of normal or healthy um, um, body temperature, right? Um, that figures into expected free energy and saying like, well, expected free energy ends up being scored over each of the policies available to the agent. That's what that G parentheses pi represents. Pi is your overall like your policies, your policy space. Each potential policy gets scored by G, and then we see that pragmatic value, that difference between the actual observations you expect given that policy versus your overall preferences. Basically, do I think taking this action is going to get me what I prefer, right? Is this action going to help me achieve a regulated heart rate or a sated hunger level or stomach or level of glutamate or otherwise. Um, or you can think of it more whimsically, like if I go to this store, will I be able to, get that dessert that I really like? Right. So that's what kind of pragmatic value is. We want to maximize it, meaning that like if I take this action, will I be able to expect that I will be able to kind of get what I want or realize my preferences or realize my priors over observations. And that's why we have that conditional the the just if you ignore the expectation in the log, it's just a probability of the sequence of observations you expect if you take this action conditioned on and thus related to your preferences. So essentially pragmatic value that's in reinforcement learning you can almost think of that as like that's sort of your reward function, right? This is how the agent is able to sort of plan and figure out, if I take an action, what observations will I be able to expect, and then I can compare them to what I actually want, and that's kind of how you score that. Meanwhile, however, we also have information gain, and this is part of what attracts me, like myself and the kind of work that I do, because some of what I do relates to reinforcement learning, in addition to computational psychiatry. I've noticed in reinforcement learning, it's sometimes very difficult to kind of handle the so-called explore exploit dilemma, which is where whenever you have a model, whether you're thinking of it as a human being who, might be suffering from some kind of mental, disorder or trouble, or it could simply be, creating some kind of robot that navigates a grid space or something. Um, it's difficult to say what should define exploration. And for those who are interested in philosophy, there's always this question of like, well, why don't people just kind of, get as many resources as they need and then just stay in their room? That minimizes all potential surprisal as much as possible, right? Shouldn't that be what we do? Um, of course, I would say like, well, if that doesn't match your preferences, then no, you won't do that. And we don't tend to prefer staying in dark rooms 24/7, but it potentially for biological reasons, but that's its own conversation, I guess. Uh, but all that is to say that with active inference, you get this like kind of nice formalized notion of what exploration is, and it's already included with pragmatic values. So whereas in reinforcement learning, what will happen is people will focus on what active inference calls pragmatic value, and then maybe you'll have some kind of rule in there that says like, oh, the agent should do something random 10% of the time just to make sure it doesn't get stuck in a local optimum, right? Like the idea of like, you know, suboptimality is sort of relative to a model as well as to the observer, right? So someone who in the case of schizophrenia, who is hallucinating, right? Like if their brain is kind of computing that hallucination, as it were, given that their brain's makeup at that time, sort of the kind of figurative generative model that it's working with to produce that hallucination in a sense is kind of optimal to that model, despite from an external observer's perspective, say a psychiatrist or a therapist or just another person would say like, oh, that doesn't seem correct relative to the environment you're in, right? So all that is to say that we have pragmatic we there's the optimality that one can kind of get stuck within, right? Um, and so it's theorized that it's through exploration that people are able to sort of get out of local optima or find increasingly, hopefully, ideally, increasingly more optimal solutions to everyday problems, and that's sort of a foundational aspect of adaptive learning. So by being able to actually have information gain as a piece of this, is kind of like saying like this is how it's saying that this is how the model works, but it also says we're not just doing something random. We're doing something that actually continues to further the goal of reducing surprise, of minimizing free energy. So it starts to kind of make more sense rather than just viewing it as some kind of random number generator process, which is like quite explicitly how that would be done in reinforcement learning models on average. So with that information gain term, it's kind of I mean it's essentially just taking the expectation of the KL divergence between here's what I so it's a Q of X conditioned on Y and pi versus Q of X conditioned on pi. So we already see like the only difference between those two things is that Y is actually incorporated into that the first distribution of those two. So it's kind of like saying, well, here's what I thought was going on, or what I think about the hit. Here are my beliefs given here's how I believe the hidden states of the world relate to what I do, my policies. Here's what I think I can do that changes the world. However, here's now what I think, how I think that works given the new observation. I apologize, I kind of got myself in a tongue twister there, but um, it's just to say, like, given this new observation, what do I think about the relationship between hidden states of the world and what I can do? So that means that by trying new things, you can try and elicit new observations that can then help you to learn more about the world, right? Which is interesting because it kind of conceptually it's almost like an inversion of variational free energy, right? With variational free energy, it's like, well, we should be self-evidencing, so we should just be trying to do essentially the same things, but in that case, we never there's no guarantee that we'll ever actually like accomplish our goals. Or come closer to accomplishing any kind of goals or preferences, whether that be homeostasis itself or it be a human being's like long-term career trajectory or some such, right? So that's sort of the gist, the overview of expected free energy, and not just like how to sort of interpret those first two terms, information gain versus pragmatic value, but also kind of understanding like that this is a very kind of self-consistent process that occurs that doesn't rely upon sort of random processes, right? Like you can try it, you can include like an error term in different places with predictive coding models, like this is the unexplained variance, but there's no forced like, oh, 10% of the time do something random. And that's sort of what some would argue would be the sort of elegance of planning in an active inference scheme as opposed to, comparison to some others. Mark, yeah, you had your hand up again if you want to go for it.
Sorry, I was on mute there for a second. Yeah, thanks. This is just another great explanation. I just want to make sure I understand this. So when we talk about expected information gain, right, we're talking about the distance between, again, sort of like prior beliefs about policies and the posterior beliefs about policy. So like as the farther these are apart, the greater information was gained through the update, and that is then inversely related to the free energy. Is that right? So there's a negative sign. So the more I learn, I guess, the bigger the update, the smaller the free energy. Is that right? So I've resolved uncertainty. Is that a fair way to look at it?
Yeah.
Okay. So I was thinking of it in terms of like there's a cost. There's entropy associated with that belief update, though. Is that right? Maybe I'm conflating
No, you're
because I'm
not.
almost there, I think.
Yeah, no, you're totally fine. And in fact, I mean, again, looking at the entire equation, it's like there are other ways of kind of sort of breaking this up. And then you see like with expected ambiguity immediately below that H, like that is where we are explicitly like looking at this in terms of like kind of entropy
Hmm.
functions.
Hmm.
But if we just constrain it to looking at it as information gain,
Hmm.
first off, yes, you're absolutely right. The idea is that if you sort of maximize or increase information gain, if you learn more about the relationship sort of between the world and observations and policies, given that there's a negative sign there, that does mean that the more we increase information gain, the more expected free energy will decrease. To briefly put that into the perspective of some of what I was saying earlier, um, if free energy is an upper bound on surprise, right, then we're going to want to minimize free energy. And so in this case, by learning more, you would indeed be reducing free energy and then
Okay.
from reducing surprisal, right? So it's, I mean, we also remember like you could improve information gain like immensely, yet simultaneously have like virtually no pragmatic value, right? Like, oh, I almost want to say like trigger warning or something, but I realized it came up with like a very dark example, but it's like, well, if someone doesn't know what it's like to, you know, I'll lighten it up a little bit, but it's still a bit dark. Someone doesn't know what it's like to be unconscious, so they're like, well, I could knock myself out, right? Like, is that you could learn a lot, maybe, maybe not. You know, realistically, no. But someone could have that belief if you just kind of localize it to this is their thought space right now. This is sort of their generative model and the problem they're trying to figure out. Like, is it truly worth it to do that in order to learn that, right? So if the answer is no, or at least if that the way that policy of knocking yourself out, if that scored much lower than or much worse off, so to speak, has much higher expected free energy than another policy which says, well, don't do that. You know, at least you get to stay alive and conscious and all of that. You know, the pragmatic value of not doing that far out exceeds the information that you might gain from doing this silly thing, then ultimately you don't do the silly thing like you did, right? So that's sort of a crude way of saying that. It's like so given that this is scored over all policies, which is another significant issue and why we use variation, like the significance of using variational methods, not just for biological plausibility, but imagine that there are a plethora of something that of actions or policies that an agent could take, right? And every single one of them is getting scored, so that there could be a ton of possibilities that are getting scored all simultaneously, right? And so for every single one of them, there's an information gain term and a pragmatic value term. So at one point in the textbook, and some people have interpreted this differently, and so Daniel and I will frequently like make a comment on this. At some point in the textbook, they claim that with active inference and kind of planning is inference in their framework, they say that sort of exploration and exploitation quote unquote naturally balance one another. And that's not exactly right because you could still have a lot of information gain, but zero pragmatic value, right? As in the silly example I gave a minute ago of someone knocking himself out or something. Um, you could have a very pragmatic, very high pragmatic value and no information gain, which someone who follows a routine can like kind of intuit. It's like, oh, this is a very helpful routine and I'm not diverging from it. So I'm never really learning anything new, but it's because it works for me, right? Or maybe you arrived at that policy and kind of chiseled it out over time. It's like, this is what my ideal day would look like, or this is what the ideal series of steps or actions I would take over the course of day would look like, maybe with some various degrees of divergence, maybe with various degrees of like, something could come up or, an unexpected events, a call on the phone, a meeting was canceled or otherwise I could get sick. But any of that. But the idea is sort of planning as inference here is just sort of over time being able to sort of discretize time into a sequence of steps and thinking of for each of these potential sequences of steps, what is there to be gained and what is there to be learned. most sort of intuitive sense. That's how I would say it. They do. So a lot of these kinds of concepts that were introduced to on so on page 37, they figure 2.6, they tried to essentially show again with the sort of interdisciplinary aspect of active inference, its relation to other fields. And so there are aspects of like control theory here in cybernetics whenever there's economics is implicated whenever we're talking about risk. So I wasn't going to break any of this down too explicitly, but in part because they already kind of do that themselves. But I was just going to refer to this for anyone who's interested in tying this into sort of other fields. And yeah, sorry, team, I noticed your hand was up. Do you want to?
Yeah, thank you. Thank you for the great explanations. I wanted to track back a little bit and maybe I have a question about the definition that they introduce at the end of chapter 3, which is related to expected free energy. And they say that a generative model endowed with temporal depth opens the door to the minimization of expected free energy, which entails at least a primitive form of agency. So, as I understand it, like the capacity to model alternative futures and to select among them to minimize expected free energy is basically what agency is, how agency is defined. Is there like more to it? Is like just the planning and the vision of the modeling of the future? Is it the only prerequisites for defining agency in this framework, or are there more, or do they go into more details into how agency should be defined, should be conceptualized? And maybe this is more of a philosophical question that is maybe out of scope for this discussion group. How does this relate to free will? Does is the capacity for planning and prospection, is it a sufficient basis for what we understand as free will, or is there something more that is required? But this is not, you don't have to answer the second question. The more important question I have is really how agency is defined, and uh, and if they go into more details on this, because it's what interests me right now. I want to really get a sense of how agency can be defined and how it can be useful for us to model, like, for example, AI systems.
Mm-hmm. Mm-hmm. All really good questions, and the way that you kind of laid all of that out in that sequential order, everything made sense. So I'm first, I do think it's a bit of a philosophical topic. Um, that is not to say that those who engage in active inference should not engage in philosophy. It's a major topic, and there are many people who are interested in active inference who want to discuss notions of agency, free will, consciousness. What does it mean to like plan or deliberate, and things like that. I think that it's been sort of conceptualized in various ways even within active inference. I think that people are kind of publishing on this in different ways, but many people have kind of commented on it. I might be able to find a couple things I could share in the chat, but there are those like Ines Ippolito who I think even Chris Fields, who's actually someone who doesn't. Ines Ippolito is a philosopher, first and foremost, who's written broadly on active inference and kind of discusses some of these things. And there are a lot of authors, sort of in that milieu who will also use it to comment upon AI and conceiving of AI and what would it mean to have agency. I would say this segment that you pointed out here in the textbook, which is on page 59 for anyone who's interested in this, which we also remember that's in chapter 3, which is the high road, which is kind of starting from sort of what it means well, let's not say means, but what it is to be an organism and to continue to exist, like adaptively survive, right? So I think that's part of why they do this like high versus low road, the low road being like a very almost strictly mathematical Bayesian framework from the whenever you first start. And then it's just from there that you can start viewing that as sort of like how we could model cognitive functions, including perception and action and decision making, versus the other direction, which is sort of like how do organisms persist? And so here we're looking at this from a very kind of organismic perspective, and then we get this comment on having a potentially a minimal form of or a primitive form of agency. Um, and I think just from what I can say is that because while I'm very interested in philosophy, I tend to do a lot of kind of computational modeling and focus sort of more on that and relating it to sort of mechanistic processes. Um, from sort of a hardline perspective, that would say like, no, there is no agency. Um, I'm not so willing, so freely able to say that. I don't feel comfortable, even though like that's not the way I should be saying that. Like that, everything's intuition now. But yeah, I mean, it's if you were able to say like, well, there are particular kinds of processes involved here, they tend to play out, aside from some stochastic, error that happens here or there, noisy observations, it's otherwise generally, deterministic or semi-deterministic. The idea of agency does sort to kind of fall out of view. That said, though, I mean, the authors here themselves are saying that there is a form of agency. So another way of framing it could be like, well, if you looked at a model that had no capacity for planning, uh, and then you just stay within this active inference framework. So, for example, we just went over expected free energy. Expected free energy is necessarily like a form of kind of planning. That form of planning relates to certain kinds of homeostatic set points that one holds, so preferences that were related in that C matrix, your attractor. So if you totally remove any kind of attractor from a system, that means that it's not attracted towards anything in particular. Well, whenever you put that into a sort of biological environment where like ideally it would be if you remove any kind of attractor from a person, then suddenly like they don't necessarily have any reason to their model can't infer that they have any reason to eat food, to sleep, to take care of themselves in any way, shape, or form. And so kind of in physical terms, like without some kind of attractor and capacity for realizing that sort of attracting state, in some way, shape, or form, you just kind of fall into entropy, right? You dissipate within your environment. Um, that relates to a notion in active inference and really a lot of other computational modeling in general, whether it's active inference or not. But it's all to say like an organism doesn't necessarily have to have a set of beliefs that perfectly match its environment. It just needs to have the right equipment for navigating that environment well enough to realize the attractions. So I'm afraid I'm getting just a little distanced from your query, but it's just to say that I do think maybe the way they frame it here makes sense. The idea of if you're able to kind of predict a little bit more into the future for making different kinds of decisions, right? Because even in like social theory or social sciences or things like that, the way or philosophy people one way of framing agency would be to say like, well, if you have no actions available to you and you have no way of trying like being allowed to choose from different available actions for whatever your own purposes are, then you don't have agency. And for those who aren't even trying to take it from a philosophical standpoint, maybe even more of a legal standpoint, like or moral standpoint, like you shouldn't remove someone's capacity, their agency, right? Everyone should be, someone might make a claim that everyone should be entitled to some level of agency. That usually does refer back to the general idea of being able to have actions that are available to you and you get to freely choose. In that case, planning would be a form like having a capacity for planning and action would be directly related to an idea of having agency. Um, I feel like if I were to speak anymore, though, I might as well just like write an essay or something. So that's kind of where I'll leave that. But I would definitely, even just a few Google searches between active inference and agency or free will and things like that. There are many people who have been very interested in this topic. It's just not my particular like area of expertise. So, yeah.
Okay, thanks a lot. But I see that there's some interest in the chat, and I'm also interested. Could you share the name of the authors? Because I didn't get you
Yeah.
said Polito or Chris Fields and Polito.
Yeah, yeah, for sure. While I'm doing that, if anyone else has any thoughts or questions they want to bring up, we can definitely get to that too.
This may be off topic, but there is a paper that's co-author. I mean, Carl is the first author on this active inference and intentional behavior. And I don't know if that's, like you said, it's maybe not exactly the thing you're thinking about, but it does discuss the difference between reactive, sentient, and intentional behaviors in simulations. So, I mean, it's not in the textbook, which I know is the topic of this conversation, but yeah, I just thought I'd mention that.
Totally. And thank you for sharing that. And I just looked it up myself and the way you described it too. It very much having not read it myself, it seems to very much relate to the textbook, which the textbook in a sense is just sort of like a snapshot of sort of where folks like Thomas Parr and Carl Friston were at in their research over the preceding decades, like up to that point in time. And Daniel and I are frankly at this point looking forward to this new textbook that will be published next year, which I think will just include a lot more that's been written since. But yeah, I mean, with intentional behavior and the way that you described, like, or mentioned, like, and that's something I didn't bring up and maybe should have. But if we imagine an organism that doesn't have a capacity for planning, it then would become a much more sort of reactive organism, and we would view it as maybe not having agency, or we would view it as not having intentional behavior. So one kind of simple example of that is to think of like a thermostat, like a control system. It's just it in that case, a thermostat does have a homeostatic set point, so to speak. We won't say it's homeostatic, but we'll say it is a set point, quite literally, like that is its design. And so if the temperature that it reads in the room as its incoming observations, if that, falls below the stat point, then the agent thermostat increases the temperature, right? But in that case, it's reactive. So it doesn't have to do with any kind of sort of, I believe that if I do this, then this will happen. It's more of a strict, like on a moment by moment basis, like purely reactive system, right? Now, what someone could do is like program some kind of decision-making process within it to where, oh, over the next hour, I'll heat up, the thermostat will increase the temperature by 1 degree. And then the following hour, it'll increase it by 3 degrees. And then after that, I'll reduce it by 2 degrees. And that's a particular sequence of actions defining a policy, and each one of them can get scored relative to some kind of attracting state. Like if it were to become more complex, then it would start to kind of look like planning under active inference, or even just planning as inference as a general scheme. Would someone want to attribute intentional behavior to that or agency? Um, I think it's around there that, like, there are those who might disagree with one another over how that should be viewed. So it's around there that I'm like, yeah, it really depends on how you want to define agency or intentional behavior. But many organisms are in fact reactive, right? Like a lot of kind of microcellular organisms are essentially just sort of floating in their respective spaces and like immediately reactive to any kind of nutrients that start to touch them or something along those lines, right? Like not necessarily a capacity for planning involved. So it's a very interesting topic to me, to say the least. I just don't have any definitive statements on what is agency. And then I'll just share. I'll try to think of any others that might come up. Um, and there's this is sort of uh, a quick way of sharing some of these things, but there have been for anyone who just kind of wants some listening material. Um, there was last year a nice series called Active Inference Insights. I just shared the link to it. It's on like streaming services, et cetera, as well. But so there are various figures that were interviewed um, by guy Darren, who was involved with Institute previously, and so he's done talks with Carl Friston and some other big figures in the area, Mark Solms, Ian McGillicrest, who's a psychiatrist, and others. And so there's a lot going on. Alexandra Rorbia, who's more into robotics and reinforcement learning. So there's kind of a nice diversity of voices from different fields. And some of them are certainly much more sort of on the philosophical side. There's Von Javis, who discusses consciousness, but relates it to information theory, but also ethical AI. So I would have a look at that. I think that's probably the quickest thing I could share with you all in a single link. And then, of course, all of them have their own respective publications if you want to dive deeper. Um, but so I see that we really hit time here, but I hope that this was helpful to some of you who are still considering, some of the topics here and the equations or formalisms or otherwise. For those who are still, kind of interested in the mathematics and breaking that down further, there will be much more to come in the coming chapters. Even more so in the second half of the book, whenever we start seeing a particular what they do is that they take different kinds of active inference simulations that have already been sort of coded up computationally and published. And so what they do is use those as sort of learning heuristics for understanding these different models. Um, and so that'll figure very strongly in the second half of the book. There's also the appendix in the back of the book that this is the author's own take on trying to sort of describe some of the basics to probability theory, such as what is the product rule, or moving up to sort of linear and matrix operations that we see in discrete time models, and um, just essential calculus and taking derivatives and so on. So there are many resources like essentially in the back of the book, and then you're just a step away from further learning those things on your own if you want to get any deeper from there. And then yeah, the next session next week at this time we will switch over to the other cohort, but anyone who is here is welcome to join. We'll talk about chapter 7, which is where we'll or excuse me, yeah, we'll talk about chapter 7, and that will be about discrete time models. So a lot of the dynamics that we saw here will actually play out. We'll have a likelihood distribution. We will have state transitions, and we'll have planning as those models. They all have this kind of temporal dimension and a capacity for planning and decision making, and perhaps even agency. Yeah, I welcome you all to that, and thank you all for coming today, and we'll wrap it up there.
Thanks so much, Andrew. When are you doing chapter 3? It sounds like you're switching over.
Yeah. There's Daniel and I do this sort of alternating. Unfortunately, it's always a
I
little
see.
confusing to like describe to people quickly, but it's essentially there's a morning and an evening session relative to I'm in the United States, so thinking of that those time zones. Uh, the in the he always does the morning, I do the evening. So 2 weeks from now, it'll be chapter 3 with this
Right.
cohort. So it's sort of we it's sort of just this back and forth.
Okay, so you'll be in the morning on the next Thursday, then you're just going to continue to flip flop more or less.
Yeah, I
Okay.
will always do the evening because that's when I'm available. But
Oh, got it. Okay.
it's essentially the other cohort is doing the second half of the book, and then
I
this
see.
cohort is doing the first half. So we have this kind of odd zigzagging between, it'll be next week it'll be chapter 7 for second half of the book. Week after that will be chapter 3, then chapter 8, then chapter 4. You see this kind of back and forth like that. But the idea is that it sort of allows us to have two separate cohorts going simultaneously for a session before we take another month or two long break. So it's just kind of it's a bit of a speed run, I guess, in that sense. But anyway, yeah. So 2 weeks from now, chapter 3. All right. Thanks so much, everyone.